everybody, welcome to another Percona Live session. Today we're going to be talking about the lost art of database design, which is a very interesting topic for me. I've noticed that a lot of people's skills are eroding when it comes to database design, and we'll talk about why. But first, a quick introduction. This is me. Hello, everyone. I am Matt Yonkovit, head of open source strategy, or the HOS for short, here at Percona. You can chat with me on Twitter at myonkovit or email me at hos@percona.com. Or matt@percona.com. I also have a podcast if you're interested in more talks by me called the HOS Talks FOSS on YouTube and at other locations. So how I want to start this is I want to talk about the current state of where we are in the database space, especially as developers and those designing applications think about databases. Let's be honest, they think databases are uncool. They're boring. Very few developers get excited when you talk about databases. If you think about a lot of the technology that they look to employ, it's to get around databases. When you're looking around ORMs, you're looking around, databases of service, what can you do to offload this? And you know who is well-versed and understands this? It's kind of the sales teams, and it's the people who are out there trying to sell you stuff and to, convince you that you don't need to worry about the database. There's these other things out there that can just help you. And, vendors out there are totally playing into this, right? So, schemaless databases, use unstructured data all you want. Oh, ORMs, you can have zero database code. It just automatically handles it all for you. APIs to do all of your data access. Native JSON, database as a service, worry about your application, right? There's a ton of buzzwords. There's a ton of things that people are looking at to try and convince you or reaffirm your concerns around the databases being boring and not having to worry about them. But the problem is you do have to worry about them. And how you build and define your application has severe consequences, right? Just like from a database perspective. It's just like a house, right? If the database is the plumbing in a house, if you don't think about making sure you have functional plumbing, you might take it for granted until there's a problem, right? And when that problem happens, and I've used this slide in a previous presentation as well, bad things happen because you can have a nice house, but if the foundation is bad, the shit breaks pretty quick, and you don't want that to happen. And so database design is the foundational element of any application. You need to make sure that it is taken care of. Because if you have a better database design, you're going to have better performance, use less space, have better security, lower your costs. You're going to have an easier time with releases. You're going to have better user experience, and you're going to have fewer outages and issues across the board. So let's talk about the basic things, the 5 most basic things that you need to concern yourself with database design and why they're important. And I'm going to tell you some war stories and some things you shouldn't do during this session. So the first is, a lot of this is going to sound like Captain Obvious. Okay? So from a Captain Obvious perspective, okay, some things you can say, and you're just like, yeah, that's totally obvious. I totally get that. But you'd be surprised how many people don't quite understand some of these things. So first, schema and design matters. Okay? This is an incredibly important thing. Okay? That schema and design matters. The right design has to understand the pluses and minuses of how you're accessing application. You have to think about your workload. You have to think about how different databases handle different types of application requests. You have to understand the growth of your application, the access patterns, how users are going to interact, right? And when you design that, you have to take into account the right data types, right? Think about the performance implications of using one over another. Don't overthink things. Don't try and out-engineer, some of the database technology that's out there, and figure out how to optimize that access with the right indexes, the right flow, the right tools that are out there. Now, schemaless is a big thing, and when I talk about schema, when I talk about database design, a lot of developers immediately shoot back at me, I use a schemaless, I use an unstructured data setup, so I don't have to worry about this. It doesn't really exist, okay? I'm going to tell you right now, schemaless is not really a thing that you want. And even, okay, the most arduent, people who are like, our vendors who are, saying, I'm schemaless, I use JSON, I use this. They still want you to do schema validation. They still want you to adhere to some structure, because when you don't, bad things happen. Okay. When we talk about schemaless, it's really about the unstructured data. Oh, I want to add columns, or I want to add, objects and not have to worry about it. Well, if 50% of your objects have, one setup and the other 50% have another, there's a performance implication to that. There's also a space implication to that. That flexibility comes at potentially a great cost. So you trade that performance, that scalability, that ease of use for flexible schemas. And so you start to run into performance problems as the data size, as the volumes increase, for queries. There's a ton there. And so you need to understand that at scale, a unvalidated schema, or one that is completely wild, wild west, doesn't perform. And it causes a litany of issues. And so you have to think through how you're going to design even your quote unquote unstructured data or your schemaless design. What sort of rules will you enforce? Because when you go completely wild, wild west, bad things happen. And so keep that in mind as we talk through some of these. Now, of course, I mentioned space. Okay, the final frontier. No, not the final frontier. We're talking about disk space. And there's this mentality out in the industry that space is cheap, but it is not free. And we've seen that the amount of data that is required for most applications or most enterprises has continued to increase exponentially. But from a database perspective, this is where you are most sensitive to the space and the space costs. Think about this. You have a 10 or 12x multiplier on the amount of space that you actually need, because you need backups, you need replicas, you need dev test systems. So when you say like, oh, I'm going to choose something and I don't really care about the space, you have to multiply that space out 10, 12 times to get what the actual cost is. And that laziness often costs a massive amount of money. In fact, I have personally seen over the last year cases where I've seen as high as 43% reduction in cost just by doing a little bit of magic around space. That's a pretty massive cost reduction. Think about that. If you're out in, go find your Amazon bill, go find your Azure bill. If I could cut 43% off of your bill and give you better performance, that's a pretty substantial savings, isn't it? And that's something that you don't need to, re-architect the entire application to take advantage of. So it's something that you need to be mindful of. Now, one does not need to look far for examples of this. I've used this example several times. There was a massive top 10 social media company that we worked with, in the past. And they keyed all of their access off of one thing, which was an email address. Okay. So, everybody's email address was in the system, and they made sure that their application was optimized so that anything you did revolved around the ability to have that email address. All the queries, everything was built. So they followed, a pretty good thought process around, we're going to ensure that this is there. But what they didn't realize is their database of choice, MySQL, uses the primary key in a way that it stores the primary key element in all the other secondary indexes. Additionally, having a textual lookup primary key does take more CPU cycles and more space. So you've got, not only space issues, you've got performance issues as well. And, it's a similar setup when you run into applications that use like a 32-bit, UUID or, other, types of things. these types of things cause potential issues because of how data is stored and how the performance of the system is. So, we actually took this social media company that was running into scalability issues, and we said, okay, well, because the application's built with the primary key, what if we added a CRC32 hash on top of the primary key, which converts it into an integer? And so we use the integer as the primary driver, if you will, and then we can do a sequence number for the rest. But you can still look up the email address, but you're going to CRC32 the email address, then give the email address. And you think that doesn't make much sense to add another column or to add a function on top of it and to have this issue. But by making some quick changes, by saying, okay, we're going to do sequence, we're going to do CRC32 lookup, we were able to, significantly reduce their cost by over 2x, and also speed up their application by, a factor of 4 or 5. Just because we changed how they were accessing all of their queries, we changed, what was stored in those indexes, and we're able to save a ton of money and cost. And when you think about from a MySQL perspective, for instance, just take a quick look, right? You've got this MySQL, right? And when you store, a varchar or a text field in a varchar field with UTF-8, that's 21 bytes, which means that, storing 1, 2, 3, 4, 5, 6 is a pretty big field, where from an int perspective it could only be 4. So you're 81% less by using the int over using a varchar. And you wouldn't generally think people would use a varchar for a numeric, but they do. And so these are common little things that you don't think add up. But when you have 100 million data points, that's 2 terabytes of data versus what could be 300 megabytes of data. And think about that if you have 100 fields that are all 100 million data points, that adds up. It's big. And then you've got that multiplication factor for replicas, for backups, for everything else. So it's important to realize what you're using there. Now, not only that, though, you've got other people who are using varchars in a way that they should, but they're not using the special data types that are available to them. So, think about storing a country name, right? So there's 200 and some odd countries in the world right now. And, it's very common for you to have a field within your database that has that column, right? What country is this customer in? Is this person in? Whatever. And not everyone normalizes that data. So a lot of times you're storing it as a raw varchar. Again, the space there is pretty large. Now, if you did normalize the data and you have an int lookup, you go from, look at the 100 data points, you go from, 3.7 terabytes of data, or gigabytes of data, sorry, not terabytes, gigabytes of data, down to 300 megabytes of data. So it's 96% less. And you can also make that an enum if you want it as well. And so that can reduce that even further. So again, space is cheap, but is it really that cheap when it comes to scalability and cost? Now, fun fact, people choose the wrong data types all the time, and people like to outsmart other people. Now, a few years ago, I was, actually this is a lot longer than a few years ago, I was at a client site where I was working on a survey system that was used in political debates, and they had a phone app that you could go in and fill out a survey on how the candidate was doing and stuff like that. And obviously this is not from that, but they had this really smart guy from MIT who was an engineer, and he's like, I want the flexibility of a super flexible schema, but I want the relational aspects of a relational database. And so what he did was he took a varchar and he turned it into a giant bit mask. And so, he stored something like this, right? 0000001, 00001. And so, it would be like, the fifth bit is male female. And the, 10th and the 11th bit are, state, I mean, like stuff like that. And so he made it into something that logically made a lot of sense from an application design perspective, but was an absolutely horrible design decision for the database because, how do you index that? How do you access that data quickly? And obviously, the design of this was really, really poor for having, 5 million people on their phones trying to fill in, data. And so that caused all kinds of issues. Now, every database has certain special data types. And you should be aware, whatever database that you're using, okay, what those are and how those work. Now, obviously, NoSQL database is a little different. That they have a lot more free form and the ability to use certain things. But when you look at Postgres, you look at MySQL, you could have enums, JSON types, INET types, lines, etc. So understanding what's available and picking the right solution to solve that is critical to a speedy, performant, and low space usage database. Now, when we're talking databases, it's also very important to think about the design patterns and the access patterns of how data is going to be accessed, because that will dictate quite a bit on how you build not only your queries, but your schema structures and your databases themselves, right? If you are going to be accessing data regionally, maybe you want to consider sharding. If you are accessing data that is only the most recent 30 days. Maybe you want to look at archiving data. There's all kinds of things that you should consider and think through how people are accessing your data. Now, indexes are part of that, right? You want to design indexes that are going to be structured specifically how your applications are accessed. I mentioned that, the social media company that we work with, everything was keyed off of an email address. So for them, they knew that every time you search for someone, anytime you did something, it would always be based on an email address. So they use that to optimize that, which means that it made a lot of sense for them to use that as an index that was always around and available. Okay. So, make sure you understand how your users are going to be querying and accessing the data, and realize that even what you assume today, it might work for a year or two. You have to reevaluate and see how the application evolves, changes, what new releases impact things. Okay, the queries and the indexes that you create today aren't necessarily the ones that you're going to need in a year. Now, my next advice here is don't be an idiot. Okay, I have been around a lot of brilliant people. I have been around people who are not so brilliant. And both of them have cases of idiocy. Okay, keep things simple. Don't overthink it. As engineers, we love to overcomplicate stuff. Let's be honest. Overcomplication is wonderful from an engineering perspective because you get to invent new things. And you want to build something that you're proud of. And so doing something that, is kind of boring sometimes doesn't scratch, engineers' itches. And so, they'll design for, the edge cases. They'll design for something, really cool. So let me talk a little bit about, the flexibility to the extreme. Okay. And so people want that flexibility. Like I mentioned, the bit mask was a good example of that. But there was another company that I worked with who built testing software to certify and test people on, different careers. So I think lawyers, accountants, so you'd go out and, you'd have to fill in your certification exam once a year and they would do that. They built this platform. They didn't know who would be certified on what things, but they wanted users to be able to come up with questions and build the sole certification platform. Wonderful. So they designed it so that everything was customized by end users. And they didn't know how many questions they would ask or how many answers they would have. So they built this thing to be just incredibly flexible. But when it came to the database design, they actually built it so it was a consistently looping kind of like setup. So it was a relational system, but it was, you you would have to check the same table for nested information. So it would be like, row number 1 with an ID of 1, has the question. And then row number 2 is a answer to the question that they could choose, like an ABC question, and it would point back to itself. And so they made it so it was this really, 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 flexible design. But they ran into performance problems because the application itself required them to loop through all of the data as each question was rendered and access that main table over and over again. And so it turned out that they would pull a row out and say, like, what's the question? And then they would go back and say, okay, for this question, let's go back to that table. And so that question, what is point A? And so they would query point A. And then they would query point B. And then they would query point C. And then they would query point D. And then they would come back and say, okay, question 2. They would query question 2. And then they would go, okay, point A, point B. And they would do this loop. And so each page that generated part of the test would actually have like 21,000, 30,000 queries. All the queries took, a fraction of a second. It was just the volume of questions was extreme. So as you think about like that flexibility, there are really good ideas to keep things flexible, but not all of them are scalable. And so keep it simple. Now, don't be an idiot. Part 2 is there are many, many companies out there in the database space, and they have done a lot of great things. But a lot of times, engineers, and I do this, I've done this, I'll be honest, I've done this a couple times, think that they can outsmart what's already out there in the database space, and instead of conforming to maybe a feature set or maybe making some trade-offs on some things, you go out and you design something that is a little bit better or a little bit more spectacular. And so I worked for this company once where I had to go in and help them, and all these problems are scalability issues. They had this problem where they were running, a load job, and the load job was just taking too long. And it turns out that when you looked at it, they decided that they did not like how database joins worked in MySQL. So they used MySQL as a pure data storage and used it kind of like as you would a document. They would read in table A, they would read in table B, and then in Java they would loop through the tables and they would join them. Don't rewrite joins, right? Databases are optimized for joins. Make sure you understand that you can use what's out in the database space and what's out in that. Don't think that, oh, well, I might want to change the database later, so I don't want to use this feature or this set. You're going to cause yourself an immense amount of pain. Now, you also have people who do the opposite, and they will conform everything to a single database, right? I use MySQL, so everything must fit into MySQL. We now live in a time when there is a tool or an application that can do a lot of different varied workloads. So don't use MySQL for things it wasn't built for. Don't use Postgres for things it wasn't built for. There are time series databases out there now that are wonderful. Use time series database if you have time series data. Use document store if you need document store type, functionality. The best tool for the job is very important, and you don't have to conform to just one size fits all. So let me recap some of this. Okay, number one, when you are looking at data access and using data, it is important that you don't think about the just in case. Okay, this is an important thing. When you're talking about, querying, when you're talking about those database access patterns, a lot of people outthink themselves by looking at, just in case. So a good example of this is using select for updates needlessly. There's a surprising number of people who do a select for update on tables just in case they may update it later on in their code. That means locking. So I've talked to our internal folks and I asked them, what is the number one problem that you would want to tell people to stop doing? They're like, don't use select for updates. It's horrible. But there's a lot of people who do that. Also, realize that as you select data, right, select star needlessly isn't a good thing either. So a lot of ORMs might do select star from table, blah, 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 blah. and then they might need one column out of that entire row or out of that entire data set, so they throw the rest away. I actually worked for a very large, top like 50 website once, who was running into all kinds of performance issues. And when we went in, we noticed that they were transferring terabytes of data back and forth between the application server and the database all the time. And when you looked at the code, they would say, select star from this really big table, and then they would throw away 95% of the data that they retrieved from the table. And so they were maxing out the bandwidth between the two. Now think about that in the cloud space, where you do pay for a lot of transfer costs, especially as you're transferring data potentially across AZs. That can get expensive. So, understanding that I shouldn't just select everything just in case I need it later on, or I shouldn't select for update just in case. It's important. But equally important is to understand how users access that data and optimize for that. And sometimes that means combining data, denormalizing, right? Data. I've done that numerous times where, it just makes more sense to, hey, instead of saving the space, I'm going to save the lookup cost. That's okay. Aggregating data. I need this aggregated for the last hour, so I'm just going to build a job to aggregate the data and then use it. Those are things that you can do. Also, the application is more than just the database. And so there are different components that are going to impact the database performance and the database setup. So are you using caching? How is that caching working? When does it get invalidated? How often is it invalidated? That herd mentality. I don't know if you've heard of the thundering herd. When the cache invalidates, everybody comes to the database. How does that work? Planning for events, understanding that impact, right? So I mentioned the testing, application that I worked on. Also, equally important with that testing application is there were times of years or during the year where all of a sudden they had access patterns they never had before. So all of their testing and all of their, failover planning, all of the, performance impact of releases, those all happen during non-peak times. So they never caught some of the performance issues, some of the issues that were designed inherently into the system, until there was a 2-week window when every lawyer in the country had to go get certified. And then all of a sudden, it's certification time, or tax season happened and you needed to get certified on the latest tax code. Those types of events drive access patterns, and understanding them is really critical to application design. Also, think about how you're going to migrate and how you're going to do migrations, code migrations, and releases. These are often the limiting factors in your application. There are tools to help with this. Also, don't think that database design is independent from the infrastructure and the infrastructure design, right? Geo-distributed clustering, backup times, how often, systems go offline for maintenance, DR tests, all of these things impact the application and need to be designed into the application as well. Thank you. I hope this was informative. Feel free to ask any questions in the chat.